We have 2 to 3 more tasks to go, then you will have a very nice Easter holiday, although you still need to stay home. And before we start, let's review what we have learned before. We have learned some the simple chemical cell, which is made of metal electrode by a pair of metal, and we can deduce the electron flow by looking at the reactivity of this metal couple. Because we know that zinc is more reactive than copper, so we know that the electron will flow from zinc to copper. Okay, this is what we have learned before. We can deduce the electron flow by looking at the reactivity of the metal. Okay, so when it comes to the metal that we don't know their reactivity, iron and chromium here, like this question we did, I bet if you don't know the reactivity, the relative reactivity of iron and chromium, then the other Form 6, Form 5 students also don't know in Hong Kong, because chromium is not even in the metal reactivity series. Then who can know their relative reactivity? Of course, no one. So at this time, if all of you don't know the metal reactivity, then you have to read the question carefully. As time goes by, the color of iron 2 sulfate solution gradually fades out. The color of iron 2 sulfate solution comes from iron 2 plus. Because only iron 2 plus has color in this iron 2 sulfate solution. Sulfate is colorless, and it said that the color fades out. That means the concentration of iron 2 plus is decreasing. That means iron 2 plus discharge, it gain electron to form iron. That means the electron is flowing into this electrode, into this electrolyte, to iron 2 plus iron. That means chromium is losing electron and giving out electron, so chromium is giving out electron. Okay, so when it comes to the metal that we don't know their relative reactivity, then you have to read the question carefully, because if you don't know, then other students also don't know, then read the question, see any hints will be given by the question. Okay, so what's new with this task now? It's chemical cells with inert electrode. Okay, inert means very stable, very stable, that they will not be involved in any reaction, they will not take any reaction. Okay, inert means you can ignore it. Okay, when we using metal electrode, the metal electrode will undergo oxidation and give out electron. Like the cases we have talked about. Chromium is more reactive than iron, then it will undergo reduction and give out electron. Oh my god. Right? Give out electron. But when it comes to inert electrode, example graphite and platinum are the examples of inert electrode. They will not react. You can ignore it. It would be just like something to conduct the electricity, to conduct the electron. Okay, when we look at this simple chemical cell, the electrode will not take any reaction. It will just pass the electron to the solution. It will just allow the electron to go to the edge of the electrode. Then what will react if not the electrode? If it's just like a rod conducting electrons, then where are the electrons going to the solution, right? Going to the electrolyte. So if inert electrode is used, if you found that inert electrode is used, then you can just ignore it. And now look at the electrolyte. Look at the solution in the half cell. Okay, so now we look at this example 1. We look at example 1. Because it's made of platinum inert electrode, so instead we look at the electrolyte. Okay, and for Ki, the electrolyte, the left half cell Ki, which is made of potassium ion and iodide ion. Do you still remember which one is the common reducing agent or the common oxidizing agent? Because now the electrode will not react, so instead we look at the electrolyte. The electrolyte must be one of them must be reducing agent, and another one of them must be oxidizing agent, and then redox reaction will take place. Then there will be electron flow. So you have to find out whether it is reducing agent or oxidizing agent in the electrolyte, and so that you will deduce the electron flow. So let's look at Ki, potassium iodide solution. Potassium ion and iodide. Can you check? No, you should not check, because you should be very familiar with it already. What kind of common reducing agent you have? What kind of common oxidizing agent we have? Okay, for potassium ion, I hope that you still remember the ECS for metal parts. For potassium, sodium, calcium, magnesium, and aluminum, and so on, they are reducing agent, and the upper one will be stronger. Okay, and they are respective oxidizing agent. Their respective metal ion, because the metal ion can gain electron, they are oxidizing agent. For their corresponding metal ion, they will gain electron, they are oxidizing agent, and the lower one will be stronger one. So potassium ion, you can see that it will be a very weak oxidizing agent, so we skip it, we ignore it. Instead, the chemicals that will take the reaction will take place, it should be iodide. Okay, and iodide, it should be I hope that you have a good memory. It's a very common reducing agent. Okay, and for the right half cell, it's made of iron 3 plus and sulfate ion. It's sulfate ion. Okay, it's sulfate ion, not sulfuric acid. The common oxidizing agent we learned is sulfuric acid, but this one is just sulfate ion. It's not sulfuric acid, so it's not oxidizing agent. And if you check the ECS, you can see that sulfate is a very, very weak. It's it's a very weak, and it's not on the table of common reducing agent and neither common oxidizing agent, so you can ignore it. Instead, iron 3 plus. Iron 3 plus is a common oxidizing agent that you can find from the table. Okay, so we know that actually it will be a redox reaction between iodide and iron 3 plus. Look at electrode P. Iodide will discharge, and as a reducing agent, it will change to iodine and completes the half ionic equation. It should be losing electron. And for the observation, the solution turns brown because iodine is brown in color, it turns brown. Iodine is formed, and from colorless, because iodide is colorless in color. And you can see that electron is giving out here, electron is coming out here. The electron comes out from potassium iodide solution, so that the electron is going to the electrode Q, because electron is coming out from electrode P, the place where electrons come out, we call it negative electrode. Okay, and so whether this half reaction is oxidation or reduction, if you still remember, oil rig can help you. Oxidation is losing electron, reduction is gaining electron, and in this case it's losing electron, so we know that it's oxidation. Okay, it's cathode or anode. If you forget, then bracket NOS can help you, because it's oxidation, and so it should be anode. Okay, for electrode Q, we know that iron 3 plus will discharge, and then it will gain electron to become iron 2 plus. So whether iron 3 plus will be reduced to iron or iron 2 plus, it depends on the strength of iodide. Okay, but iodide is not a very strong reducing agent. It will only reduce iron 3 plus to iron 2 plus only. Okay, so the solution turns, what's the color for iron 2 plus? It's pale green. So it turns to pale green because of iron 2 plus from yellow, because iron 3 plus is yellow in color. And opposite, it should be positive, and it should be reduction, and it should be cathode. And for the overall reaction, for the left half reaction, only two electrons are involved. When it comes to the right, only one electron is involved. So the right hand side one should multiply by 2, and the overall equation should be, okay, done. Okay, it's done. So what's happening here? This is a redox reaction we have learned between reducing agent iodide and oxidizing agent iron 3 plus. So what's going on here? Why we can get electricity from it? In chapter 30, we know that the redox reaction will take place between these two chemicals. So if you mix these two in test tube, then the redox reaction will take place, and the chemical energy will change to heat. That means the test tube will turn warm because the chemical energy is turned to heat. But because they are very reactive reducing agent and reactive oxidizing agent, so if you mix them, they will react directly. But if you separate them into two half cells, like here, if you separate them to two half cells, they want to react with each other a lot. The electron wants to transfer between them a lot, but you separate them, then they cannot react directly. Instead, if you connect them with an electric wire and salt bridge, then the electron can flow through the electric wire from the reducing agent to the oxidizing agent. So the redox reaction can still take place. Okay, but they are not reacting with each other directly. Instead, the electron will pass through the electric wire, so that they can react by allowing the electron to pass through the electric wire. So the chemical energy will be changed to electrical energy. Okay, in this case, it will not change to heat, but it will change to electrical energy. Okay, so that's why we said we have before this chapter we learned the redox reaction. Okay, actually it's a reaction between reducing agent and oxidizing agent. If you mix it in the test tube, then they will react with each other directly. But if you separate them and connect them with electric wire, then they can still, the redox reaction can still take place, and you can get the electricity from it. Okay, so to sum up, it's a redox reaction taking place in the simple chemical cell, And because they use inert electrode, so we look at the electrolyte. Okay, so you have to do example 2. See, they use graphite, another kind of inert electrode, so we look at the electrolyte. Find out which one is the common reducing agent, which one is the common oxidizing agent, then you can reduce the electron flow. Okay, so you have to do example 2, example 3, example 4, and you can try example 5, but it's quite difficult. We will do it in the next step. Okay, and exercise 2 on page 41 and question 1 on page 42. Okay, so you will do this question first, and you, of course, you can try example 5, but example 5 is quite difficult. Okay,